Okay, so the next question, part 3, says that the shop is doing a quality check of all of their chocolate bars. They select 10 chocolate bars at random, okay? Find the probability that this sample has a mean weight of less than 145. So we need to think now. We're no longer working with this distribution anymore because we're looking at a sample of chocolate bars, in this case a sample of 10. So in other words, we're going to have to translate or basically change this distribution to, instead of just talking about one chocolate bar, we need to talk about 10 chocolate bars. So we're looking for the mean of those 10 chocolate bars, okay? So, are you happy it's still going to be normally distributed? If we have 10 chocolate bars or just one chocolate bar, if the one chocolate bar is normally distributed, the 10 chocolate bars will still be normally distributed. What's the mean going to be? So it was 150. What's the new mean going to be when we consider these 10 chocolate bars put together? 150, isn't it? Exactly. So 150 stays the same. The mean stays the same. What's the variance? What's 5 squared? What's it going to be now?
5 squared divided by 10.
Good. So it's going to be the old variance divided by the sample size, which in this case is 10. Good. This is just simply the central limit theorem, right? And we've talked about this at great depth in the past. Basically, the idea is that as n increases, as you consider more and more things, the sample mean should approach what the true population mean should be. And the spread of the distribution decreases, and it decreases by a factor of n, right? So the variance decreases by a factor of n. So this is now the new distribution that I'm going to be using. So now I'm looking for what's the probability that this distribution has a mean weight of less than 145. So what's the probability that x bar now, the mean weight of these 10 chocolate bars, is less than 145. I'm going to do exactly the same process as before. So I'm going to say, okay, z will be equal to, well, I need to take the mean, so I'm using this distribution now. I can basically ignore this distribution. So I'm taking this distribution, taking the 145, taking away the mean, and dividing by the standard deviation. So it's not going to be 5 squared over 10, it's going to be 5 over root of 10. Oops, let me. There we go. So dividing by the standard deviation, it's simply the square root of 5 squared over 10. Square at the top, square at the bottom. Okay, so this is going to be a non-integer. So do you want to just quickly type it in your calculator, see what you get, John?
Minus 0.316.
Negative.
Negative 0.316.
Okay, great. Now in the tables, we only need 2 decimal places. So I'm just going to call that 32, just for the sake of not having confusion. Okay? So in other words, when I jump over to my tables, I'm going to be looking for the probability that z is less than negative 0.32, like so. So let's figure out what that is. So I'm just going to pull up my tables. I'm going to use the negative 0.3 row, which is that one there, and I'm looking for 0.32, which is going to be 0.3745 is the probability. So if you like, that's about 37%. And once again, if you did just wanted to verify that, just come over to GeoGebra. Obviously you're going to have to change the standard deviation now to be 5 divided by square root of 10. Oops, there we go. And I'm looking for 145. Less than 145 is going to be... That's different, isn't it?
Oh, sorry. It's minus 3.16.
Ah, that might make sense now then. That's all right, don't worry. Okay, so this was negative... Oops, throwing things everywhere. Negative 3.16. Okay, so yeah, when we jump over to our tables, we're looking for negative 3.16. Okay, and our tables came out as, well, I've got it on the screen, 0.0008. So that's about 0.08%. Okay. And actually that does make sense, because if you think about it, for values which are further away from the mean, the probability of obtaining them should decrease as the sample size increases, because the spread of the distribution decreases as well. So with our x is just 1, we get a distribution that looks like this. Okay? And then as n increases, this is what we should happen. So the distribution literally becomes more peaked. In other words, for a value like 145, which is out here, are you happy that when we're just dealing with 1, we had a higher probability? Okay? But then as soon as we had more things in our sample, that probability should decrease, which makes sense because the probability of obtaining values further away from the mean, as the sample size increases, should decrease as well. Okay? You've got less chance of obtaining a value which is not the mean, basically. Right? So hence the reason why that has to decrease from what we had last time. But actually, I'm really glad that happened because it highlights the importance of just having this in the background, yeah? Because it's really quick and easy. It's literally just a case of just typing a couple of numbers in and it's there in front of you. So if something comes up differently, as we go, oh, that doesn't seem right, then you can just quickly go back and check.